Greetings, everyone. Let's go over the homework for elementary mechanics. So this is one type of the problems that I will ask on the quiz. And most of these problems are dealing with gravity field, but of course they are all related to Newton's second law. So let me write that up first. Newton's second law. Honestly, I don't know what his first law is, but I did look it up. So the formula is very compact, but of course there's a lot going into there. A is the acceleration, and for us A will always be the derivative of velocity. We will try to solve this in terms of velocity, so that it would be a first order equation. If we would want to solve for y, then it's a second order, which is something we will learn later. And then what is F? This is the force. And this depends, of course, and m is the mass, and F is the force. And that depends on the given situation. So, as I said, most of these are dealing with gravity, but here's an example, number 3, where you use it in a different way. So we have I'll read the question for you. I'm sure you have read it, but a boat weighs 64,000 pounds. Its propeller produces a constant thrust of 50,000 pounds, and the water exerts a resistive force with magnitude proportional to the speed, with proportional constant 2,000 pound per second feet. Assuming that the boat starts from rest, find its velocity at function of time and find its terminal velocity. Okay, so the picture is we have, well, the boat is on water, right? So here's my little boat. I'm very bad in drawing. So here's I'll make it a sailing boat, but it has an engine. So it goes this way. So what is the force here? Gravitation, you might say. No, gravitation doesn't play in this, in the sense that we're not going downwards. We're resting on the water, right? So we're going horizontal. So what is the horizontal force is given by an engine that is 64,000. That is the engine, but there is the water resistance makes us slow down. So that's why it's a negative sign. So it's always very important to have the sign here. So why do we have a positive sign here? Because it's the engine that pushes us forward. It's not an engine that tries us to slow down. That could be too, right? Sometimes if you see these ferries, when they start getting to the landing, they basically reverse their engines so that they slow down that way. But that's not the case here. We're going forward. And so what else? And we have the resistance force, and it was proportional to the speed with proportional constant 2000. So 2000 V. Okay, so let's plug everything in. Oh, no, 64,000. That's sorry, I took the wrong number. The propeller is a constant thrust of 50,000. So that's 50,000 here. For those that, okay, so we have m v prime equals 50,000 minus 2,000 v. What is missing m? So what is m here? The mass, that's the 64,000 you say? No, remember, there's a difference between mass and weight. So let me write it up. What is weight? Weight is the force that the mass exerts when on, well, for us, of course, on Earth, but this can depend on where you are. And so in some of the problems, weight might be at a different planet or in a different gravity, where the gravity is different, right? So for instance, if the gravity 0g, I'm sure you have heard of 0g, right? No gravity. What does that mean then? That you don't have mass? And of course you have mass. It's just you don't have weight because you're just floating, right? So weight is really m times g. So in this case, we have 64,000 is m. And what is how should we measure g here? Everything is in pounds, and so it is the ancient the British system. So this is 32 feet per second square. And so from this, we see that m is 2,000. Okay, so we can plug this in. 2,000 v prime equals 50,000 minus 2,000 v. Clearly, we can divide everything by 2,000, so v prime, and then what we have here is 25 minus v. It becomes a very neat differential equation. What do we do with this? Remember, this is actually a linear one. So you could here, you could do the first the homogeneous and then find the particular solution. But this is also separable variables already. Okay, this is a very simple, it's a constant one, because here even this is constant. And in that case, don't do this extra step of going first the homogeneous and then the particular. You can separate the variables. So these are separable variables. I write it here. So it's not just not because it's a linear one that you'd always have to do it that way. This is quicker this way. So this would be, I write this as dv, and then this becomes a dt here, right? And I bring everything to this side. And why? Because this is very easy to integrate, right? So if I derive this, that is ln 25 minus v. Now I have to be careful here. If I derive with a negative, it's a negative v, right? So if I take the derivative of the ln, I get 1 over, but I get an extra negative 1 here because of the chain rule. Now I don't want that extra negative 1, so that's why I put another 1 there. They cancel on each other out. Okay, so this is equal to t plus a constant. So let's call this constant. Now, when you converting ln's, you can, when there's a coefficient in front of it, you can bring it inside, but you can also bring it to the other side. And I think in this case, I would always do that, suggest you do that, because if you bring it inside here, especially if this would be a number, we'll see the next question, then this becomes a big power, and it's very hard to work with powers, right? But if you bring it to that side, then you don't deal with that. So this is ln 25 minus v equals minus t minus k, but I'm going to rename k. So I put it between quotes. This is not the same k, but it's almost the same k. Now I can I exponentiate. I see this is 25 minus v equals e to the minus 2 plus k. And that one, we know what to do, right? This is an ek to e minus t. And this would becomes my new constant c. So we find, let me write it up, 25 minus v is equal to c to the e minus t. Let's see, so far so good, I hope. Yes. And what do we need? This is the c here. That's the integration constant. We have to determine what it is. How do we do that? So the initial condition, it said at rest, at t was 0, it was at rest. So v was 0. Okay. So what does that mean? 25 minus 0 equals c to the e to the 0. And so we see that c is actually 25. And therefore, what we get is, I should have solved for v here, perhaps. So let's bring the v to one side. So v is equal to 25 minus 25 e to the minus t, or if you want, 25 1 minus e to the minus t. Let me double check here. I want to show that I didn't make any mistake. I hope by now you have figured out that there are I told you this already, right? That the answers of all the problems at the back of the book. But that is not always that useful because it doesn't tell you how to get to the answer. And especially if you make a mistake, you don't know, am I really wrong or I just made a silly mistake in the end or some small thing. Okay, so this is our velocity. And there was an extra question. What is the terminal velocity? So with terminal velocity, let me remind you. This is the velocity. So this is what we did. And in some sense, it's a theoretical concept because we can never have infinite time. So we'll never reach that terminal velocity. But what very often happens is that fast enough, we get close enough to this terminal velocity. It's a limit, and we know that limits tend to go towards their value that they are, and very often rapidly. So to do that, so this is a theoretical concept that tells you at least after a while, and the while might be dependent a bit on the question, could be a long while, but very often it's just a short while. What is almost the velocity? That's what terminal velocity stands for. Okay, so let's calculate this here. Limit, this is for t going to infinity, 25, 1 minus e to the minus t, but this is very simple, right? If I plug in infinity here, that is e to the negative infinity, that will be 1 over e to the infinity, 1 over infinity, that is 0. So this goes to 0, and we see that this is 25. And it's positive sign here that, again, make sure that everything works as it's supposed to be. Why? Because we are going in the right direction. So yes, in our picture here, this was our x-axis, right? So that's why we wrote everything, that this was a plus sign because we were going in the direction of x-axis. This was a negative sign because we were, the resistance works works in this direction, in the opposite direction. Okay, so you see here, this is an example of mechanics, not but not gravitational. Let's go to the gravitational question. Sorry. Which was this 4.3, right? Number 10. So number 10 says we have an object that weighs 256 pounds and is dropped in a medium that exerts a resistive force with its magnitude proportional to the square of the speed. So we are on the surface of Earth. It doesn't say that explicitly, but okay, that's understood. Unless they really say, oh, you're somewhere else, we are on Earth. So we are on the surface of Earth here. Well, let me not. It's not it's gravitational, but we're not going into space. So I'm not write too much space here. But what we do is we have a container with a certain medium liquid in there. Say they make not very clear what it is. It could be a gas. It could be something like that. But we are dropping something inside here. Okay, so we are dropping this object, and this object has 256 pounds. It weighs 263 pounds. It starts from rest, and what we know is, let's write down the formula again. F is ma. What is F here? Well, F consists of two parts. It's the gravitation pull, that is m minus g. Remember, again, keep reminding you that our y-axis always, the y is the position, right? Y is always pointing upwards. So we are going down. That means gravitation always pulls you down against that direction. So that way we write minus mg. That is the gravitational force. But there's another force that is the resistance force. What does that do? Does that help you go faster, or does it help the object go faster or slower? Slower, right? Because the force works with the direction of the y-axis, so you get a plus sign here. So, and it says proportional to the square of v, of the velocity. Okay, so what we need is g. We know what is mass. So the mass, remember the mass is had this formula here, right? Weight is m times g, so that is 256 pounds. So g again is 32 here. Is 256. So it's very lucky that this gravitational constant on Earth in pounds is actually a very nice number. It's 2 to the 5th, so it's a power of 2. And you're going to see we're going to have a lot of powers of 2 coming in this problem. So this is 2 to the 5th. So that is m is 256 divided by 32, which is 8. Okay, and k, what is k? Well, k, they say, is, we need to find k, right? We still don't know what k is. Sorry, write it that way. Well, we know that the force if the velocity is 4, yeah, if the velocity is 4, then the force is equal to 1. So what does that mean? If I plug this in this, so this is the formula for our resistance force, right? Okay, plug it in, so k times 4 squared, 16 is 1, so we see that k is 1 over 16. Okay, we have everything, so let's write down what we have. M, A is v prime. Oh, m, we know what m is, sorry. Okay, let me write down the formula again. So this is what we're dealing with, right? Let me write it out and then fill in the constants. Then let's see, it doesn't come, where does everything come from? Okay, so we have m v prime, I'm writing a as v prime already, equals minus mg plus kv squared. That is our differential equation, and we know that m is 8, v prime is equal to minus 256 plus 1 over 16 v squared. And again, this is a separated variables. I don't like the fractions, so let's multiply everything with 16. Now these are powers of 2, and that so 8 is 2 to the power 3, 16 is 2 to the power 4, and 256 is 2 to the power 7. No, 8, right? To the power 8, yes. So I'm doing that because it's going to be easier if I write just powers of 2. believe me. So I'm going to multiply both sides with 16. So this is my 16 times 16 and that times 16. So these two cancel, that is okay. What is 16 times 8? You can work that out, but it's 2 to the 4th times 2 to the 3rd, so that's 2 to the 7th. V prime is equal to 16, then this, that is 2 to the 4th times 2 to the 8, so that's 2 to the 12th. Sorry. Okay, 16 is 2 to the 4th, and that's 2 to the 8th, so together add the exponents to 2 to the 12th. So minus 2 to the 12th plus v square. Okay, so bring everything, the v's to one side, the t's to the other side, but the t's, there's nothing, everything can be brought to the other side, so we get the 2 to the 7 dv is v squared minus 2 to the 12th equals dt. Okay, now we end the derive. What is the left-hand side here is, I'm sure that you don't like the fact that I write this 2 to the power 12. That might throw you off. If you don't do it like that, spell out what it is. It's 4096 or something like that. But see, what I have to do now, this to integrate this is a rational function, this is integration by parts. Integration by parts. So let me do this separately here. It means that I have to write this fraction in its partial fraction. Integration by parts, I'm so sorry, that's not what it is. Not at all. I see these words are so similar that I got confused. It's in partial fractions. That's what I was gonna write down over there, right? So it's partial fractions, of course, sorry. Parts, integration by parts, partial fractions, I got confused there. So this is, we have to write this, we know, well, first of all, we have to factor this guy. But this is a difference of squares. This is actually v minus 2 to the power 6 times v plus 2 to the power 6. The difference of squares. Then you have to, this is the square of 2 to the 6, right? But the square root is dividing the exponent by 2. So this is how this factors. See, it's easier to see the factorization that way. And it means that I can write this here as a certain v fraction with in the denominator v to the minus 26 plus b v plus 2 to the 6th. Okay, so let's find a and b by clearing the denominators here. So multiply this and multiply this, both with that. So what we have left one is 2 to the 7th equals a. Here we have a v plus 2 to the 6th left, right? Plus b, and there the plus guy cancels, and we have this guy left. Okay, and now we plug in the roots. Plug in roots. That means if v is 2 to the 6th, that is one of the roots, then the second term disappears here. This term is now 0, right? And so we get, if I plug it in here, I get 2 to the 6 plus 2 to the 6. That's twice 2 to the 6 is 2 to the 7th. See, it's so easy to work with binary numbers. 2 to the 7th is a 2 to the 7th. Oh, look at that. These cancel and see that a is 1. Aren't we lucky? And so what happens with the other one? We plug in, this is plugging in this root. If we plug in the other root, is the negative one, right? Then the first term disappears, the one with a, which we know already, so there's 2 to the 7th is equal to b, and now we plug in minus 2 to the 6th, minus 2 to the 6th. So twice 2 to the 6th, minus, that is 2 to the 7th. So this is minus 2 to the 7th b, and so we see that b is 1. Okay, so sometimes, although these numbers look ugly, they are really chosen so that it becomes actually nice. So let's go on. So this means now that if we antiderive this, then it is 1 over v minus 2 to the 6th, minus 1 over v plus 2 to the 6th, that is the b is negative 1, right? Oh, yeah, b is negative 1. I wrote 1 here, but I said negative 1, but I wrote it wrong, right? Okay, so now we're good? Yes. Okay, dv, and that is equal to the antiderivative of this thing, which is t plus a constant. Okay, we take the antiderivative, that's just ln's. We know that we have to combine this ln because we have to solve for v, so we have to kind of bring everything v together, right? Ln, and the difference of ln's is taking, oh, no, not squared there. V minus 2 to the 6th divided by v plus 2 to the 6th that is equal to t plus k. Then now we exponentiate. So v minus 2 to the 6th over v plus 2 to the 6th, which is, by the way, 64, right? I think now I should spell out what it is equal to e to the t plus k, and we split this as e to the t times e to the k, and this becomes our new constant, so c e to the t. So writing down, we get v minus 64 over v plus 64 equals c times e to the t. And to determine c, we need the initial condition. And they told us that we actually drop. So drop, of course, means that it is from rest. Okay, this means that v was 0 when t was 0. So we plug this in. We get 0 minus 64 over 0 plus 64 is c to the e to the 0, which is 1. And so this, the left-hand side is negative 1, so we see that c is negative 1. Okay, so where are we? We have our v minus 64 over v plus 64 equals minus e to the t. Now you might say, Professor, shouldn't we have first solved for v? This is still explicit form. But solving for v doesn't change anything, right? It's just rewriting the equation. I know, so this is sometimes a little bit confusing for students with why you use a k here and then you name it c, because this is an ugly way of writing a constant. This is easier. But once I've kind of settled on, I say, now I'm not going to change this c anymore, this constant anymore, I'm not going to rename it, then I can calculate it, right? And why do I do this? Because it's actually easier to plug in. Now, if you don't want to do that, let's just solve for it. And how do you solve? Well, okay, it makes it easier now because I know what c is. Otherwise, in fact, it makes it a little bit harder. But finding c sometimes is harder because you have to keep writing what it is, and it's -1. Otherwise, if you write c, it's easier. But okay, so I'm bringing this to the other side, right? And I'm going to bring this to the other side. So I get v minus 64 equals minus e to the t v plus 64. And I expand this. That is minus v e to the t minus 64 e to the t. Bring the v to that side and this 64 there and that to there. So you get v plus v e to the t equals 64 minus 64 e to the t. So here I can factor out the v. 1 plus e to the t equals 64 can factor out here 1 e to the t. And so finally find v is equal to 64 1 minus e to the t over 1 plus e to the t. Okay, this is our velocity. And again, we might, I don't know, did he ask? Yeah, if I also asked the terminal velocity. So the terminal velocity, again, it's here it's really theoretical, right? Because in the previous case, you could say, okay, the boat can go on forever, although, of course, it cannot, because there's going to be a shore at some point. Here, even less so. If we drop this in an ocean or in a tank, when it hits the bottom, that's the end of it, of course, and the velocity is just 0. But again, it's a theoretical concept that tells us very often, especially because we have these exponentials here, that we're going to get to this velocity very quickly. Okay, so how do you take this limit? Let me very quickly go over that. The limit for t going to infinity, 64 1 minus e to the t over 1 plus e to the t. So there are two methods. So method 1 is L'Hopital's rule. Yeah, but what you normally do, of course, you should try to plug in. But if you plug in, you get infinity over infinity. And that is one of these L'Hopital undefined forms, indeterminate forms, sorry. So this is, let me write this here. It's an indeterminate form. Now you have to be careful. L'Hopital doesn't solve every indeterminate form. It has to be one of the form infinity over infinity or 0 over 0, which is the case. So what we do then is we take the derivative of the top. Now the 64 is there. What is the derivative of 1 minus et? Well, that is just minus et, right? And the derivative of the bottom is et, and we have to take the limit. But there's not really much limit to take here because a lot of things cancel out. So I get minus 64. Okay, these two cancel. So that means that after infinite time, it would fall down at the speed of minus 64. Whatever our units are, feet per second, I guess. But although we'll never reach actually that velocity, very soon we will get close to this velocity. Even if we're talking t equals 3 or something, I think we are very close already to what the velocity would be. This is minus 64. Now, method 2, and there is perhaps a little trick here is to try to make it not in an integer form, and what I'm going to do is multiply top and bottom with the same thing, e to the minus t. But of course I have to multiply everything to e to the minus t, so I'm going to write the result already here, okay? So we get 64, then we get e to the minus t, e to t and a minus t cancel, and in here we get e to the minus t plus 1. Now, if I'm not mistaken, in the back of the book, that's actually the form that they give, that they write the solution. So you might already be saying, well, wait, I found this, and this is what they say, but you see it's actually the same. And that is sometimes very difficult in this kind of questions, is to see your form compared to the form that somebody else found, because depending on which steps you do one at what time, you can get something that looks differently, although it isn't differently. And why is this now a better form? Why did the book write this? Because the terminal velocity is now very easy. If I plug infinity, this goes to 0, this goes to 0, and so we see immediately it's the same, minus 64. So we get minus 64. Okay, so I'll do a bit more in the reviews of this type of problems. Let me point out a couple of things to be very careful about. One promise: numbers will always be nice to a certain extent. Of course, there are sometimes inevitable some fractions, and inevitable perhaps even some square roots or something like that. But to the extent that the numbers are not enormously bad or big, if there's something like that is happening, stop, perhaps pause a little bit and go back to the problem. Because if you go to the problem right away, you still might think about some number that is supposed to be something like that and actually something else. Okay? Sometimes it's best to let it rest a little bit and think about, or let your mind calm down and go over it again if the numbers come out a bit weird. Also, pay very attention if your integration comes something impossible. So again, something might wrong. Signs are little things, but they're very important. Always see the forces. Is it working within the direction that I'm going or against the direction I'm going? And that is very extremely important here in order to solve these problems. Okay. All right.